Marco Giordani is assistant professor at University of Padova. He has a long experience, considering that he's a young age, on the implementation of mobile networks and research in the area of mobile wireless networks more in general. And the tutorial today will be on 5G new radio specifications. Of course, we've been discussing a lot of 5G and the application of 5G. But again, some of the characteristics of 5G are really associated to the characteristics of the radio interface. And with Marco, we will have an overview of the characteristic of the 5G new radio and how the different the type of traffic and behavior of the radio interface can be matched with the applications. So Marco, the floor is yours.
Right. Good morning, good afternoon, everyone. Thank you, Antonio, for the nice introduction. So as Antonio just mentioned, my background is on protocol design for wireless networks. And indeed, today I'm here to talk about 5G networks from a standard point of view. I would take this 1 hour more or less to review what the standard is about, as long as 5G is concerned, and focus on the most interesting, because of time constraints, aspect in this sense. First of all, I would like to start by presenting the 5G use cases. And I have to warn you that this slide dates back to 2015, when actually a few years before 5G was formally standardized. And you can see that some of these use cases are now being used to promote the next generation of wireless networks, of cellular networks, that is 6G. But okay, I mean, some of these use cases didn't actually see the light in the time frame of 5G, and so they are being used to advertise what's next. But still, we can see that in general, the main goal of 5G was to provide better connectivity, meaning higher throughput, lower latency, and better reliability under different aspects and for different sectors. You can see here some very important applications like massive use of Internet of Things, extreme real-time communication and this tactile internet, pervasive video streaming and video applications. So there are many ingredients at stake here. But in general, if we want to categorize these use cases in some groups, the 3GPP has proposed these three main classes of use cases for 5G and relative requirements. And so we have one class that's this EMBD, where the goal is to have very broadband connectivity with very high data rates. That stands for enhanced mobile broadband. And then there is another class that is referenced to as URLLC, which means ultra reliable low latency communication. In this case, the goal is no longer on the throughput domain, but more on reliability and latency and low latency. And finally, there is this MMTC class that stands for massive machine type communication, in which the use case is neither on throughput nor on latency, but actually on the number of connected devices that we want to support within our network. So you can see that there is just already one big issue that you have to deal with when 5G design is concerned. And this issue is that we have different use cases with different requirements and most likely conflicting priorities. And so the goal of 5G will be to provide and to support all of these pillars, all of these groups together at the same time. And we will see that 5G has been designed with this objective in mind and in order to address this concept of heterogeneous networks. If we focus a little bit more on the use cases that 5G is intended to provide, we can compare them with the use case, the KPIs and the requirements of previous generations, especially 4G. So now in this light gray color, you can see network requirements for 4G. And in the dark gray color, we have these 5G network requirements. And we can see that network requirements are expected to improve under many different metrics. We need to provide very high data rate for the end user, an increase by a factor of 10. much better support for mobility, better spectrum efficiency, and also this very low latency concept, which is particularly challenging to address, considering that the goal is to have a latency which is in the order of 1 millisecond, which is 10 times lower with respect to what 5G networks have been designed to support and provide. You can see that in order to satisfy these very strict requirements, network operators, vendors, and consumers have to agree on the way 5G networks look like and the way they will be eventually implemented and finally commercialized. And this requires a very thorough and accurate standardization process that has started a few years ago for 5G and is currently in progress right now. And for instance, in this slide here, you can see how has been the evolution of the standard for cellular networks over the past few years. In general, standards are agreed upon by the 3GPP, the Third Generation Partnership Project, which is a group of companies and research institutions which aim at standardizing the behavior and the technology behind each mobile generation. And we can see from this slide that we have had around one new generation every approximately 10 years. And right now we are in 2025, and we are in the middle of the actual 5G specification with all of the different releases. If we take a closer look at the 5G standardization process for the 3GPP, you can see that right now we are heading towards release 19, which will be officially released by the end of this year. And the first release of 5G was actually standardized in 2019, so almost 6 years from now. So many innovations and many advancements have already been formalized with respect to the very early 5G generation. And we expect the next releases to be even more advanced and innovative. And we are heading towards 6G, which will be possibly released in 2019 as part of release 21. And most of the things I will discuss in this tutorial today are relative to the first early version of 5G as it came out from release 15, even though I will give you still some possible discussion about how some early proposals have been eventually improved in the new releases. So in this slide, you can see where the standard is going today. And we can see that as we go towards release 19, we are already talking about 5G advanced, which is, let's say, an in-between 5G as the way we intend it and what 6G will be like. And if you can see, if you look at this slide, so the standard, the way the standardization process works, in general, it works in a series of steps. First of all of the groups of individuals and companies that attend the 3GPP meetings come with some ideas that they want to include in the standard. And then there is this PSG meeting, a plenary meeting that gathers together all of these entities, and they together gather to approve study items, which are some sort of items that are particularly relevant and that then company are then required to study further. And the output of the study item is a technical report, which is indeed what is finally agreed to convert into what is called work item, which is indeed the next step for the development of the features that will be see the light in the standard with some more detailed implementation parameters. And so these technical reports are eventually executed in the 3GPP technical specifications, which is what you can read if you want to know how the standard looks like. So just for you to have a very brief overview of the standard, I'm reporting here in these slides a few of the most critical and important and popular 5G technical specifications for the standard relative to the requirements in this slide. Here there are some other documents relative to the radio access network and protocols, and most of the things I will discuss today are taken from these technical specifications. And then if you're interested to something related to the core network, for example, there are also here some other technical documents that you can refer to if you want to further improve these ideas. So here are some technical documents on the some parts of the core network, and here are some others. I will not spend time on that, but it's just for you as a reference. So before we actually start with the more technical part of this tutorial, I just want to make one claim. So at the end of the tutorial, you may realize that 5G products that we find and that we buy, especially smartphones, we buy 5G smartphones, and we have been buying 5G smartphones for many years now. So these products are quite different with respect to what the standard is about. And there is a joke, a rumor that says that odd number generations like 1G, 3G, and 5G for cellular networks are, let's say, they are quite bad with respect to even number generations like 2G and 4G, which are good. So it looks like 5G may also go along these lines in the sense that many of the things and many of the very good innovations and pieces of research that have been standardized within the actual technical specifications of 5G didn't actually see the light in the commercial products. This may be due to the fact that today, we don't really, for most of the applications we use in our everyday life, we don't really need the good benefits and the boost in terms of capacity and data rates of 5G. And this is not stimulating network operators and vendors to actually invest effort, time, and money into implementing in the products 5G innovations. In other words, we can use our applications with small innovations with respect to 4G networks and previous generations. So this is just a disclaimer to say that many of the things you will see in this tutorial today are very good pieces of research, but right now are not totally seeing the light in the final products. And hopefully by the end of the tutorial, this claim will be more clear. So that's a tentative outline for today. I'm saying tentative because I have to admit that this tutorial is part, so I built this proposal up based on a course that I teach at the PhD program on 5G, which is a 20-hour course. So I had to squeeze most of the things to fit in 1 hour. So I had to make a choice on the things to talk about. And I'm not sure I've been so good in that. So that's the tentative outline. Let's see how time goes and what we can actually cover. I will do my best to cover at least the first 3 points. So general overview of the radio access network architecture and data plane and control plane. A brief discussion about the 5G spectrum and the use of massive MIMO. And then some more details about the 5G NR frame structure, the concept of numerology in time and frequency domains, and duplexing. If time allows, as I hope, I will also briefly discuss 2 very important protocols and protocol procedures at the medium access control layer, specifically beam management and scheduling. And then I'll conclude with some indications of where the standard is going towards 5G advanced and 6G. All right, so let's start with a general description of the 5G NR architecture. So just to give names to things, so 4G is, in 3GPP nomenclature, is referred to as long-term evolution, while 5G is referred to as new radio. And this standard introduces new innovations and new technologies to support new use cases with different and diverse requirements, as explained earlier. So there have been many innovations have been formalized in the standard since release 15. Here is a general overview of the main innovations. There is a personal list based on my personal preference of the innovations that have been introduced and that I believe are particularly nice for us as researchers. But for time constraints today, I will just focus on a subset of these innovations. And in particular, I will talk about the concept of scalable numerology and flexibility. I will say a few words about MIMO. Then we'll talk about dynamic TDD and duplexing, which is something new. And then I will do some other discussion about the concept of dual connectivity. So in order to give an overview of how the 5GNR architecture looks like, so we know that in general, the system architecture can be split in two parts. We have the radio access network part, which is what we do mostly as, so if you are in the telecom domain, you mostly work with the radio access network to design, to implement radio network functionalities like scheduling, resource allocation, dealing with retransmissions. And most of the things I've discussed today are indeed relevant to radio access network. But then there is also the core network, which has been redesigned in 5G with a new name, which is 5G core. And the core network is basically responsible for interconnecting with as a bridge between the internet and the radio access network, and then for authentication, connection setup, and also to deal with security constraints. As long as the 5G architecture is concerned, so the name that we give to the base station in 5G is GNOD B, compared to the name that we assigned to the base station in 4G, which was eNode B, that's the evolved Node B. And the new, besides this change of name, to discuss it, to refer at the end of the day to basically the same things, there is a new innovation that 5G introduced, which is the concept of the split at the GNOD B. So one GNOD B can be split into two components. There is a DU, there is a CU, which is the central unit, which gives support to a set of the GNOD B DUs that stands for distributed unit. So the idea is to split the stack functionalities of the GNOD B into smaller components, which are indeed the DUs. The idea behind this approach is to save energy and also to simplify the structure of the network, because the idea is that the DUs only implement a limited subset of the stack functionalities with respect to CU. So DUs are easier to manage, easier to deploy, faster, more energy efficient, and also more cost effective. And this is a very good and scalable solution, especially for network operators. The other very good part is that once you is under the control, so once you controls many DUs and all of the user equipment that are connected to the DUs, so this allows for some centralization. One DU can manage and optimize the control of the network for all of the DUs it is currently supervising. So there are many benefits of this approach, even though there is a drawback, we can say that is that the CU, it's a full-blown, a full-stack GNOD B, but because of the fact that it needs to support a very large number of DUs at the end of the day, the complexity of managing and to administer this CU can be quite large. So there is a very good, a very open field line of research, which is to optimize this split. So to optimize the number of DUs that can be under the control of one single CU. And this is something that, in order to avoid bottlenecks and to avoid some congestion in the link between the DU and the CU. But this is something that is nice to at least mention here. 5G also gives names to the interfaces that connect the different parts of the architecture. We have interfaces between the GNOD B, the radio part, and the core network, which is the NG interface. There are some XN interfaces that are used to connect the GNOD Bs one another. Generally, this link is realized through some high capacity, almost ideal fiber optic connections. Then there is this F1 interface, which is, in case you do the split between CU and DU, the F1 link is the link that connects the DUs with the CU, and it is what we want to avoid being overwhelmed with too many traffic requests. And then there is the UU link that connects the GNOD B to the UE. And this is for the radio access network part, and most of the times, the link for us is indeed this UU link. The 3GPP also defines some connectivity scenarios. There are many options that the 3GPP has standardized, even though we have one distinction to make. So the architecture can be either standalone or non-standalone. Standalone in general means that there is only one single type of GNOD B and network entities that is used for the network. So it can be only 5G or only 4G if we talk about previous generations. While instead, the non-standalone architecture permits for two different types or for more than one node to coexist together. This can be, for instance, two base stations of the same type, so two 5G NR GNOD Bs together, or one 5G NR GNOD B that connects together with one 4G eNode B. There are many reasons why we may want to go for this non-standalone connectivity option. So if you have, for instance, two base stations of the same type, this can promote better diversity, and it can also improve the probability of receiving data well if, for instance, you connect together with both. So if one of the links fail, you can use the other one to still serve the traffic, and you will avoid some network outage or some connectivity failures. On the other hand, the reason why you may want to use together the 5G GNOD B and the 4G eNode B is in order to deal with the different types of traffic. So one approach is to use the LTE eNode B as a sort of master base station to deal with the connection to the core network and for dealing control traffic, while instead you can use the 5G GNOD B for the data part to boost the data rate and to improve the robustness of the network. Right now, the 3GPP is giving higher priority to option 3, which is this dual connectivity non-standalone paradigm in which we have together the 4G eNode B and the 5G GNOD B. And then the next priority 2 is going for option 2, which is instead of totally standalone 5G NR only architecture. This is more complicated to arrange because today many protocol implementations still rely on 4G networks. But yeah, the idea is to go one step further and come up with some totally standalone network deployments. So moving forward in terms of the protocol stack, well, we distinguish, first of all, between the user plane and the control plane. The user plane is generally handling data transmissions, while instead the control plane is used for transmitting control messages to handle the configuration of the radio interface connections. So like how to set up the connection, how to assign resources, to give some feedback and information about the quality of the communication. So it simply doesn't involve the transmission of real or useful data, but it is just there for handling, of course, the correct operation of the network. So as long as the user plane is concerned, the 5G radio access network architecture consists of 5 different layers. There is only one, so one new layer is introduced in 5G, which is this SDAP, Service Data Application Protocol, while the bottom layers are taken from 4G LTE design with some modifications in terms of functionalities, of course. So let me briefly go through the details of these layers and the goals, so the roles they have in the network. So I'll start with the SDAP, which is this new layer that is introduced in 5G. The idea is, so this layer is used to handle data transmission, data transfer, we should say, from the upper layers, so from the core network, to the lower layers, specifically to the underlying PDCP layer. So why do we have to introduce this sort of middle layer between PDCP and the core network? So the idea is that we have to consider the fact that 5G comes with different use cases and different requirements and possibly different types of traffic. And these types of traffic have to be possibly treated in a different way, depending on the requirements they have to satisfy and the way the network is expected to address those requirements. So the SDAP is a layer that marks different types of traffic with different labels depending on the QoS requirements they are expected to satisfy. So once we assign different types of traffic with different QoS labels, and we mark them as different QoS flows, when the lower layers will receive this traffic, they know how to treat them, they know which protocol parameters to set in order to satisfy the QoS requirements that have been previously determined. We didn't have to do that in 4G and previous generations, because in previous generations, there was basically only one type of traffic, so there was no need to filter out different classes, while instead in 5G, because of this concept of heterogeneous networks and heterogeneous use cases, we have to introduce this middle layer. The rest of the protocol, the rest of the layers are very similar to 4G. We have PDCP, which is in charge of header compression and duplicate removal and in-sequence delivery, we can say. RSC is responsible for segmentation of packets and for dealing with retransmissions. Medium access control layer is basically for scheduling, resource allocation, and HRQ. And then we have the physical layer, which deals with the transmission, modulation, and stuff. But so the only very new concept is this new SDAP layer. As far as the control plane is concerned, we have this physical MAC, RLC, and PDCP layers, and the actual layers that we are more interested in are the RLC, that's the radio resource protocol, and the NAS, so that's the non-access stratum. So just a few words about NAS. So NAS is a control layer which is in charge of handling with the connection setup, mobility management, paging, and security. But for time constraints, I would rather focus a little bit more on RRC. That's indeed this radio resource protocol. So RRC is used to, so it supports 3 different states for the user equipment when it is in the network under the coverage of a certain GNLB. So there are these 3 states are idle state, connected state, and inactive state. Inactive state is a new concept that has been introduced in 5G. So idle and connected. So when the user has some data to send to the GNLB, it is in a connected mode. It has a physical link connection, a UU link connection with the GNLB, and this link is used for sharing data, for exchanging data. If the user has no more data to send, it is allowed to switch and go to an idle mode, which is a sort of sleep mode in which the user doesn't have an active connection to the GNLB. It only receives some paging signals just for mobility management purposes. And it's not allowed to send data. But on the good side, it is saving a lot of energy because it is in a sort of dormant state. So this is what we generally have in 4G and previous generations. The problem is that when you go from the idle state to the connected state, this process involves some power consumption, and you shouldn't go too many times between these 2 states to save energy. So considering that in modern internet, there are many applications that instead generate bursts of data, it would be more convenient to add a new class of state, this inactive state indeed, in which it is much more convenient for the user to go from a dormant state into a connected state. So when the user is in the inactive state, it still doesn't have a direct UU link connection to the Genome B. So it is still not allowed to send data to the network. But on the good side, the switching to the connected state involves a much lower power consumption. And it's much more convenient for the user equipment to switch between the connected and the inactive states many times. I have to say that, of course, energy consumption in the sleep mode is a little higher with respect to what you would have in the idle mode per se. But at the end of the day, it is much more convenient to stay in this inactive state, especially if you plan, according to the statistics of your network, to generate frequent bursts of data to simplify the switching to the connected mode. So that's a general description and overview of the 5G architecture. Now, before we go to the next part, which is the technical description of the spectrum and frame structure, I would like to spend a few words to give you a general, we can say, formula that can be used to estimate the maximum data rate, we can say the capacity of the network, between two nodes, between the Genome B and one user equipment. So the reason why I'm giving you this slide is not for, we can do that. We can use this equation to compute the data rate, that's for sure. But rather, I would like to shed light on how many parameters we have to set and tune for this purpose. So in other words, the data rate that we can have between the user equipment and the Genome B depends on a very large combination of parameters. Just to briefly mention them, so we have this J. So J is the number of carriers that we can use if we go for a carrier aggregation type of approach in which we can combine different parts of non-consecutive bands, and the 3GPP standard says that this capital J can be up to 16, so we can together aggregate together up to 16 carriers. And what's within the brackets is relative to just one single carrier. So then other parameters are V, which is the number of layers that's used for the MIMO architecture. Q, that's for the number of bits for the modulation, and we can go from Q equal to 1, that's for BPSK, up to Q equal to 8, that's for 256 QAM. Then F, that's a scaling factor, which is less than 1, actually. Sometimes we want to downgrade the performance of the system, deliberately downgrade the performance of the system to maybe save energy if the user doesn't have strict connectivity requirements to satisfy. Rmax is the code rate, and then there is this other part in this red rectangle, and that's for the nominal data rate, which depends on the number of resource blocks and the bandwidth. And then there is this OH term, which is the overhead for the signaling. This is what we would like to reduce as much as possible to limit the impact of the overhead. So many different parameters. Just if we give some numbers, that's a possible use of the parameters. We have, for example, that the user data rate is in the order of 300 megabits per second. This is with this very specific combination of numbers. But the idea is that as you play with your parameters, as you fine tune the network configuration, you can get different numbers. And this table is a summary of the performance that you can get at the in 5GNR in terms of data rate as you change the configuration parameters. So the last row of the table is the reference benchmark for LTE, in which the maximum data rate, I'm talking about the capacity of the network, is limited to around 100 megabits per second, while instead in 5G, we can increase this number a lot, up to gigabits per second, which is in line with the requirements of many of these 5G applications that I showed you at the very beginning of this tutorial. So why am I saying that? So first, because we can see that with 5G, we can really improve network performance, in this case, in terms of data rate with respect to 4G and previous generations, which is one of the goals of 5G. The reason why we have to go for a new generation of cellular networks. But also the other reason why I spent some time to talk about this is because we can see that there is a keyword that we should remember as far as 5G is concerned, and this keyword is flexibility. 5G has a lot of degrees of freedom, and many parameters we can freely change and set depending on the requirements of the application we want to support. This flexibility is a killer feature for 5G, even though at the end of the day, we can say that it probably didn't go as expected, giving all of this flexibility to network designers, but this is a discussion I would like to keep for the very end of the talk. And so just bear in mind that we have the flexibility to do almost everything as long as we play with the 5G and our parameters. And the 5G standard gives us the freedom to do so. And we will see this concept of flexibility coming up many times in the rest of the tutorial. Okay, moving forward, let's spend a few words to talk about the 5G NR spectrum. We all know that spectrum is a key resource for every radio access network. We need the spectrum to communicate. And in particular, we need a lot of spectrum when we want to communicate a lot of data. And since one of the main pillars of 5G, at least from the radio access network part, was to improve the data rate of the communication, one idea was to increase the communication frequency, and so to go to some higher spectrum bands. The main idea behind this going higher in frequency is just because when you go higher in frequency, you also can use a higher bandwidth. And with a wider bandwidth, you can possibly send data faster or better or more efficiently. And in fact, if we take a look at the spectrum allocation, that's the spectrum allocation for different wireless services in the US. I couldn't find a similar picture for Europe or Italy, so that's why I'm focusing on the US in this toy example. So that's the spectrum allocation from 300 megahertz on the very top left part to 300 gigahertz on the bottom right part. And we can see that here in blue is where most of wireless networks that we use today, like 4G and previous generations, Wi-Fi, and many others, are located. And in this part of the spectrum, since it's quite short, there is a maximum bandwidth that we can use. And in 4G, the maximum bandwidth is 100 megahertz with the carrier aggregation. Actually, the standard supports up to 20 megahertz of bandwidth per single carrier. But if you aggregate multiple carriers together, even though non-consecutive, you can go up to 100 megahertz of bandwidth, which gives the data rate that I showed you earlier, which is around 100 megabits per second or so. So it's quite good and okay for many of the applications we use, but still quite limited. The idea is that the rest of the spectrum, this green part that I've highlighted here, is mostly unused, or, well, there are many services that use this spectrum, but there is a lot of empty space that we can use for establishing cellular communications instead. And in this part of the spectrum, the bandwidth that we can use is up to 2 gigahertz. So as you can see, it's 20 times higher than what we can have with 4G and previous generations. And so the idea for 5G is to increase the carrier frequency in order to exploit a much wider bandwidth and establish some more efficient communications. And 5G supports this idea. And in particular, it comes with the possibility to operate through two different so-called frequency ranges. So 5G connections can be established in the frequency range 1, which goes from 400 megahertz, more or less, up to 7 gigahertz or so. And also there is this new type of frequency range, which is frequency range 2, which goes from 24 gigahertz up to 55 gigahertz in release 15, even though now in release 17, this number has increased up to 71 gigahertz. This part of the spectrum is also generally referred to as millimeter wave bands. So we can say that 5G networks can operate either in the legacy spectrum below 10 gigahertz or in the millimeter wave spectrum. There is also, and I'm saying that as an informal knowledge, that there is some discussion about a new range, that is this range 3, which is also referred to as mid-band, which goes from 7 to 24 gigahertz. And this is not officially part of the standard specifications for 5G, but since there has been a lot of discussion, since these bands are quite promising from a propagation point of view, it is quite likely for FR3 to appear in the standard quite soon. So if we take a look at the frequency bands, how they have been allocated in the world, you can see that many countries use and establish 5G services in both the frequency ranges. So there is a part of the bandwidth of the spectrum around 3 and 4 gigahertz, and also in the 6 gigahertz spectrum, which is dedicated for 5G transmission. And then there is also this other new band between 24 and 30 gigahertz, which is specifically within FR2, that is used for network connections. Focusing on Italy, for example, you can see how different network operators are selling 5G services to the customers according to different bands. And in fact, a few years ago, Italian operators participated to these spectrum auctions for buying some spectrum capacity in FR2. They invested billions of euros for participating in these auctions and for having the possibility to use the licensed spectrum for selling 5G services. Even though the standard supports communication in FR2, as you can see from this table here, most of operators today sell the 5G service in the legacy FR1 spectrum domain. And indeed, even though formally promoted in the standard, the use of millimeter waves and communication in FR2 is not so popular in general. And it was the adoption of FR2 for communication was slower with respect to what was formally expected for many reasons. One is because at the end of the day, most of the applications don't need this very large bandwidth, which is provided by FR2, but most likely because communication in FR2 is not cost-free. There are many benefits in terms of bandwidth, in terms of data rates that we can achieve. But from a propagation point of view, communication in FR2 is quite challenging. And there is one big problem of that, which is actually two. One is the path loss, which is experienced at high frequency in FR2. And the other one is the blockage. So in terms of path loss, this formula here, it's the so-called freeze propagation loss formula, which relates the receive power with the transmission power. And as you can see, this relationship depends on lambda, which is the wavelength, and on r, which is the distance between the transmitter and the receiver. And the receive power decreases with respect to the transmission power with the square of the distance and with the square of the frequency. Meaning that as we increase the carrier frequency, we also decrease the receive power at the same distance. So if we want to go higher in frequency to benefit from the very large bandwidth that we can have in FR2, we generally have to reduce the transmission power, the communication distance, in order not to lose too much receive power. And this is one problem for cellular networks, because reducing the communication range means to increase the density of network deployments, which is not cost-free either, because it costs a lot for network operators to arrange. And this is something the network operators are not willing to do. And the other problem is with blockage. I'm making a strong simplification here, but the idea is that the signal can penetrate through some solid material up to the wavelength. And since as we go higher in frequency in the FR2 domain, the wavelength is quite small. And the reason why FR2 is also referred to as the millimeter wave spectrum is because the wavelength is indeed in the order of a few millimeters. We can say that the signal can penetrate loss-free through some buildings by a few millimeters only. Or if it does penetrate, the attenuation because of the blockage of the solid material is quite severe. So in other words, if we operate in FR2, we necessarily have to communicate in line of sight. So there should be a line of sight between the transmitter and the receiver. If there is something in the middle, the signal would get strongly attenuated and we may lose the actual link between the user equipment and the GNOP, which is another very challenging aspect to consider in terms of network design. There is one way in which we can possibly solve this problem of additional path loss in FR2. So if we take a look at the freeze formula again, the actual complete freeze formula is this one. So we can compensate for the additional path loss experienced by the short wavelength by exploiting the antenna gain. And antenna gain by beamforming can be realized by using some massive MIMO technologies. So briefly, by simply putting together multiple antenna elements rather than just using one single isotropic antenna. And these multiple antenna elements, if the signal is shifted properly, we can shape beams in certain directions of the space and concentrate the same transmission power in just one single specific geographic location of the cell, which will benefit from the resulting beamforming gain and compensate for the path loss with very good receive power values. There are many advantages of using massive MIMO. So today we don't have time to discuss massive MIMO, but I know that one of the Restart tutorials was specifically focused on massive MIMO. So I would refer you to this tutorial in particular. But in general, the idea of using massive MIMO is to benefit from this resulting beamforming gain. If we, again, apply a strong simplification, the beamforming gain generally goes as the log between the product of the number of antenna elements used at the transmitter times the number of antenna elements you use at the receiver. Again, this is a strong simplification. The actual equation for the beamforming gain follows a much more complicated electromagnetic shape that I didn't report in this slide, but the idea is that as you increase the number of antenna elements to use, you increase the beamforming gain as well. Even though at the same time, you also decrease the beam width of your beam. So maintaining the alignment between the user and the GNB becomes more complicated. And this is one of the issues that we have to deal with when we use 5G, when we establish some 5GNR operations in FR2 using massive MIMO. And if there is time at the end of the tutorial, I will spend a few words to talk about that as well. All right, so moving forward with the next topic, we have we have this new 5G NR frame structure that introduces the concept of flexible numerology. So when we talk about numerology, we basically refer to three different things. So numerology is the combination of the subcarrier spacing, which is the size of one single segment of the spectrum, the cyclic prefix, which is the a piece of a set of symbols that is put between two OFDM symbols to reduce inter-symbol interference, and the length of the symbol duration. In other words, the subcarrier spacing can be seen as the size of one subcarrier, or the size between two different peaks of the spectrum. The cyclic prefix is the length between two consecutive OFDM symbols, and the length of the symbol is eventually related to the subcarrier spacing. So I'm going quite fast on this part because what I want to focus on is mostly related to the frame structure. So the way this concept of numerology is used to define the frame structure, both in the time and in the frequency domain. So let's start with what we do in 4G LTE. In 4G LTE, the structure of the frame in the time domain is basically fixed. There is a fixed subcarrier spacing equal to 15 kilohertz, and there is a fixed cyclic prefix equal to 4.7 microseconds, even though there is also an extended version of the cyclic prefix up to 16.7 microseconds. But at the end of the day, we can say that these two numbers are fixed. In 5G instead, the idea was to give some variability in that sense. And again, it returns the concept of flexibility. And so we can freely change the subcarrier spacing, and so the corresponding cyclic prefix, as well as the length of this UFDM symbol, based on the type of scenario we're considering, based on the network requirements, based on whether we are operating in FR1 or FR2, based on the size of the cell, based on the KPIs we want to satisfy. So based on many things, we can choose freely the subcarrier spacing, and so the numerology. And this has a strong impact on the frame structure. Let's see why. So that's the frame structure in 4G LTE. So in 4G LTE, we have fixed frames of a length of 10 milliseconds. The frame is split in 10 subframes, each of which has a duration of 1 millisecond. And then every subframe is split into two slots, and that's again another fixed number, where each slot is of 0.5 milliseconds. Then each slot is further split into a number of OFDM symbols, either 7 or 6, depending on whether we use the normal cyclic prefix duration or the extended cyclic prefix duration. So except for this flexibility in the duration of the cyclic prefix, everything else is fixed, is predefined a priori, and cannot be changed. On the other hand, in 5G, we have a different approach. The approach is the following. So we introduce 5 different numerologies from 0 to 4, where 0 is that of LTE, where the subcarrier spacing is fixed to 15 kilohertz. And then as we increase the numerology, we also increase the subcarrier spacing from 15 kilohertz up to 240 kilohertz. And the idea is that as you increase the subcarrier spacing, the corresponding duration of the OFDM symbol decreases accordingly, from a maximum value of 71 microseconds in numerology 0 down to a value of only 4 microseconds in numerology 4. As we can change the duration of the OFDM symbols, we can also change the duration of the slot. And so the number of slots we can fit, we can pack in just one single subframe. In other words, in 4G LTE, the number of slots per subframe was fixed to 2, In 5GNR instead, the number of slots per subframe depends on the duration of the FDM symbol, so on the numerology. Let me give you a brief example to clarify that further. So again, we have the frame with of 10 milliseconds, 10 subframes of 1 millisecond each. Then the number of slots in the subframe depends on the numerology. With numerology 0, the duration of each OFDM symbol is 71 microseconds. There are 14 OFDM symbols in one single slot. And it means that in 1 millisecond, we can only fit 14 of these symbols, so just one single slot. 71.35 times 14 gives 1 millisecond. So with numerology 0, in one subframe, we can fit only one slot. As we go to numerology 1, the duration of one single OFDM symbol is reduced to only 35 microseconds. It means that since one slot consists of 14 OFDM symbols, one slot has a duration of 0.5 milliseconds. This means that we can fit 2 slots in a 1 millisecond subframe. As we go to numerology 2, the duration of the FDM symbol is 17 microseconds. So the duration of one slot of 14 symbols is 0.25 milliseconds. So we can fit up to 4 slots per subframe in 1 millisecond, and so on. So as you can see, as we increase the numerology, we can increase the number of slots we can fit in one single subframe. And this is the last column of this table, or the column with the slots per subframe. We can go from 1 slot per subframe with numerology 0 up to 16 slots per subframe in numerology 4. This is a key innovation of 5G with respect to previous generations, because as you can see, compared to 4G LTE, we can freely change and arrange the time domain structure of the slot based on this tuning parameter of the numerology, which is a very good innovation. We can apply a similar paradigm also to the frequency domain. So in the definition of the resource block, in 4G LTE, the resource block was formally defined as a set of 12 subcarriers in frequency and 1 slot in time, so 7 or 6 OFDM symbols. And so as you can see, in 4G LTE, there was a strong relationship between the number of subcarriers we can use in the frequency domain and the number of symbols we use in the time domain. The innovation of 5GNR was to remove this interaction and to define the frequency domain, so the resource block, only in terms of the subcarrier spacing. So we don't have a binding between the time and the frequency domains, but the resource block is defined only in terms of the number of subcarriers it consists of. And one resource block consists of 12 subcarriers. This is taken from 4G LTEs, but with no implications in terms of the number of slots or the number of symbols we have to use in the time domain. So for example, you can see that the resource block size goes from a minimum of 180 kilohertz with numerology 0, since the subcarrier spacing is 15 kilohertz, up to a value equal to 2 megahertz, 2.8 megahertz, when we use numerology 4, and so when the subcarrier spacing is 240 kilohertz. So again, you can see a very strong impact of the numerology, and in the same way in which we can arrange different types of slots depending on the numerology, in the same way we can arrange different formats of the resource block based on the value of the subcarrier spacing we set. So this concludes more or less what I wanted to talk about regarding the frame structure. And unfortunately, as I warned you at the very beginning of the tutorial, I wasn't good enough to fit much more topics in this 1 hour. So unfortunately, because of time constraints, I don't have the chance to go through some other description of the medium access control layer and beam management and scheduling. So for the sake of time, I will stop here with the bibliography for today. And if you have any questions, of course, I'm happy to address. Thanks for your attention.